When you learned integrals in Calc 1, you looked at the integral from one point to another, like a definite integral. Say you have, so in Calc 1, in Calc 1, let's call it Calc 1. All right, so you had this a to b of, say, f of x dx. This is just single integral. So this, our region of integration, I'll call it region, but in actuality, the correct terminology would be the interval will be from a to b just on the x-axis. So this is your interval of integration, okay? And then your function f of x, for instance. Now, you now learn, so let's change this to single variable, single integral, single integral. That's the correct, that's what I was thinking of. All right, now we looked at double integral. Double integral. So we had integration over a region of f of x y dA. A is just a notation. A doesn't mean anything other than the fact that our interval our of integration now becomes a region of integration, and we're integrating over the area of that region of integration, area. So A is kind of for area. All right. So in this case, you have your region of integration is on the xy plane. Maybe you have something like a region like this. I'm going to make the region more general, not totally a square or rectangle. I'm running out of words. So maybe we have our function is something like this. Let me draw the function first. The surface of the function, and this is x-axis, y-axis, and you have this function, and then this is your region of integration, maybe something like this. You're integrating over this region. Call it R. Your region of integration. So your interval becomes a region, okay? Now, notice that this region, when we evaluate this integral, we have to do more. Set up the region, set up the integral from x to y, from maybe a to b, or a function of x and a function of y. So this becomes, we need to be able to change this to dy dx, and then we need to figure out what goes here, what goes there, and what goes there, and what goes here. So it's it involves setting up. Other than this one, for single integral, we just get the two bounds and we go ahead and evaluate it. But in this case, we need to set it up. But that's not our focus here. My focus is to show you how we progress, how an interval, if you, from a function of one variable, if you now go to function of two variable, it becomes a region, and then function of three variable. Triple integral is what we're doing today. Triple integral. In triple integral, we're going triple integral. Our region of integration is now a volume. It's now like a B. It's let's call it, it's like a volume. It's like a 3D region, you know. And the notation is usually B. Some people use E. You see a lot of notation. Some we use D, you know. But B comes from box. It kind of feels like a boxed region, you know, instead of like an interval like this. All right, so you have f of x, y, z now. And instead of dA, it becomes dv, v for volume. Now, triple integral, the region of integration, the region of integration, is interesting because it now becomes like a region like this. So maybe a region like this. This might be your B. Something like this. Can be any other thing. Yeah. So this is your region of integration. Call it B. So this is your X. This is your Y. This is your X. This is your Z. Okay. So when you set it up, you end up with three different single integrals. So maybe you get dy, you get dz, dy, dx, something like that. Okay, so let's do an example. Let's do an example. Let's try one. First one. So we would like to evaluate the integral b z dv. Our function of three variable is just z. Our f of x, y, z is just z. All right? Where E is the solid tetrahedron. So our region of integration is a solid tetrahedron bounded by the four planes x plus y plus z equals 1. All right, so I'm going to sketch our region of integration. It's actually this, this tetrahedron. Okay. It has four faces, but it's a solid. And this is this is 1. The intercepts are 1, 1, 1. This is z equals 1 minus x minus y. And I just got that from this equation of the plane. So it's four planes. Oh, I didn't write all the planes. X plus y plus z equals 1 is one of the planes. X equals 0 is another plane. Y equals 0 is another plane. Z equals 0 is another plane. I'm sorry about that. So this is the first plane. Then the next plane is when x is equal to 0. So that's one plane. So I'm going to call this plane 1. So I can just label it plane 1, plane 2, plane 3, plane 4. So this is plane 1, this plane right here, the triangular plane facing us. Plane 2 is the one on the triangle on the YZ plane. So that's plane 2 right here. And this is plane 3. Plane 3 is a triangle on the ZX plane. That's plane 3. And plane 4 is the triangle on the XY plane. Plane 4. Okay? So we have 4 faces. But that's not how we're going to look at it. We're going to look at it, we're going to try to describe this this solid using equations, and we're going to look at it based on the limits or the bounds along the x-axis, along the y-axis, and along the z-axis. So let's start with the z-axis. So we're going to call this is our E. Oh, I used B and then I used E. Sorry about that. So let's use B. Let's use B. B. You can use E also, or D, whatever. All right. So let's look at this. We have E is the region. This is our E, the region E. This triangular tetrahedron, 4 faces, is E, is a set of points X, Y, Z. Now, we're going to first of all describe the Z part of this equation. Where does Z go from? Z, if you look at Z, Z starts from the floor, which is the XY plane, up to the plane Z equals 1 minus X minus Y. Think about it. It doesn't start from the XY plane to 1. Nope. It starts from the XY. It's bounded along the Z axis. It's bounded by Z equals 0, which is XY plane, and is bounded by the plane Z equals 1 minus X minus Y. All right? So on Z, we're going 0 is less than Z is less than 1 minus X minus Y. Then we now have to deal with X or with Y. Y, look at this line. I'm going to make it green. Y starts from the x-axis, starts from this line. On the y-axis, you have this green line, and then you have this line, okay? So if you want to maybe visualize it better, you can look at your y-axis and your x-axis, and then you see that green line I'm talking about, okay? That's the green line, and this is another green line. This is X, this is Y. So Y goes from Y equals 0 to this line, which you can think of Y is equal to 1 minus X. Okay? Actually, Y equals 1 minus X. So you have 0 is less than Y, is less than 1 minus X. And then you're left with X. X just goes from 0 to 1. X, 0 to 1. Now, with that, we're able to now set up our integral. I'm going to move this to, no need to move it. We can now set up our integral. This integral, B, I called it B and then I labeled it E. I don't know what's wrong with me. B, Z, dV becomes a triple integral. And we're going to start with the Z. You usually start with the variable that in order to express that variable, you need the most number of variable. What do I mean? So our function is Z. We know that. It's a very simple function. It could have been Z, X, Y, tangent of 5X plus 2Y, stuff like that. No. All right? So it could have been any function, but it's just Z. Right? It's a very simple function, Z. So we're going to start with the Z, which has nothing to do with this Z. It's just a coincidence. All right? It has nothing to do with this. All right. So we're going to start with the z-axis, along the z-axis. Along the z-axis, z goes from 0 to 1 minus x minus y. So z, to express z, we need two variables, x and y. So it has to be the most internal, or the most inside, the most interior integral. Now we go to y, which has one variable, x. So it goes from 0 to 1 minus x dy, and then we're going to do 0 to 1 dx. All right, what am I talking about? Most number of variables. You really have to start with the integral that needs the most number of variables. This has x and y, two variables. This has x, one variable. This has no variable, just a constant. 2, 1, 0. Okay? So that's how you do it. If you don't do it that way, it's going to be wrong. So we do our integral, which this integral should be easy, but let's try and do it together. I'll do it until I get bored, and then I may tell you the answer and we go from there. Let's start with the most interior integral. So if you take the antiderivative, it's 2 squared over 2, z squared over 2. You go from 0 to 1 minus x minus y, and then you still have dy, and then you have 0 to 1 minus x, and then you have 0 to 1, then you have dx. So if you plug in 1 minus x into the integral, 1 minus x minus y, you get 1 minus x minus y squared over 2. And then you plug in 0, you just get 0. Okay? So you're going from 0 to 1, 0 to 1, dy dx. And then you can actually expand your stuff, expand your 1 minus x minus y, and you go from there. So and then you just do the double integral. So let's see, is there any quick way of doing this? There might be a quick way of doing it. I don't know. Okay, let me see. I'll try something. If it doesn't work, I'm just going to erase it. I'm going to try use substitution. All right, the easy way to do it, or the most non-sophisticated way, is to just expand this. Expand it. Multiply it out, FOIL it, But I don't want to FOIL it. I'm going to do use substitution. I'm going to say let u be equal to 1 minus x minus y. This might not work, but who cares? If it doesn't work, we'll try something else. Du dx or du dy is equal to -1. This means that du or dy is equal to negative du. Okay? Now, I have to look at my bounds of integration, because I'm making a use substitution. So I got to change this bound, and I got to change this bound. All right? So I'm going to say when y is equal to 0, what is u? U is 1 minus x, right? And then when y, no, this should be 1 minus x. 1 minus x. I just went from 1 minus x to 1. Okay, it should be 1 minus x. All right? So when u is 1 minus x, when y is 1 minus x, when y is 0, u is 1 minus x. And when y is 1 minus x, what is u? When y is 1 minus x, u becomes 0. Isn't that very interesting? So I went in here. I wanted to change these bounds, this and that, because I'm now going to be dealing with u. All right? I said to myself, oh, u is 1 minus x minus y. When y is 0, the lower bound of integration, u is 1 minus x, obviously. When y is 1 minus x, which is the upper value of integration, the upper limit, u is 0. So now I go back to my integral. What does my integral become? This integral now becomes, it goes from when y is 0, it is 1 minus x. And when y is 1 minus x, it is 0. And remember, this is our u. 1 minus x minus y is u. So this becomes u squared over 2. And then dy is negative du. So we have du, and we throw a negative outside there. And we're going from 0 to 1. And then we have dx. Okay? So it makes it look a little easier, a little more doable. So now we can now do let's do the inner integral, which becomes now u cubed over 6. And then you're going from 1 minus x to 0. And you still have dx, 0 to 1. So when you plug in 0, when u is 0, so you still have your negative. When u is 0, what do you have? You have 0. When u is 1 minus x, so you have negative integral 0 to 1. So we plug in 0 and you subtract when you plug in 1 minus x. So it becomes negative 1 minus x cubed over 6 dx. So this is actually integral 0 to 1 minus x cubed over 6 dx. So we can now do another u substitution. We can still call it u, or we can call it v. Let me call it v because we've used u. So we can say let v equals 1 minus x. So that dv dx is equal to negative 1, which tells us that dx is equal to negative dv. All right? When x is equal to 0, v is equal to 1, right? V is equal to 1. And when x is equal to 1, v is equal to 0. So things are going to be flipping, and we now have integral v cubed put over 6. Let me not put it. And then we're going, instead of from 0 to 1, we're now going from 1 to 0. 1 to 0. Because when x is 0, v is 1. And when x is 1, v is 0. So we have v cubed over 6. dx now is negative dv. So we put dv here. Put a negative there, right? So this becomes v to the 4th over 24th. V to the 4th over 24. And then you plug in 0, you plug in 1, put a negative here. When you plug in, 0 and 1, 0 at the top, 1 at the bottom. When you plug in 0, you have 0. When you plug in 1, you have 1 over 24. And your answer is just 1 over 24. So this is your final answer. Final answer. 1 over 24. All right. So we did a bunch of u substitution, which you could avoid by just expanding, but I just saw it and I'm like, oh, why not use u substitution? Okay. Now let's look at another problem. Okay. So number 2, we would like to evaluate the integral b x y z squared dv. I'm using b here. I don't remember what your textbook uses, to be honest, but I'm going to use b. All right, I think it uses b, where b is x y z. All right, x is between, I want to say x is between 0 and 1, y is between -1 and 2, z is between 0 and 3. So this region is actually a box. It's like a box. That's the region of integration, the solid of integration. You can actually draw it if you want, but we're not going to waste our time drawing it. It's a box. I would like you to draw it. Try drawing it, okay? But it's a box. Z goes from 0 to 3. Y goes from -1 to 2. And x goes from 0 to 1. Okay, why not? Might as well draw it. Okay. So 0 to 3, -1 to 2, and then 0 to 1. Okay, 0 to 3, I'm gonna go 1, 2, 3, and then I'm gonna go -1 to 2, pop, 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 and then 0 to 1, that. So this is a box. Like that. And then now this is the moment of truth. The moment of truth is this. It is that. And then this. The moment of truth. The moment of truth. All right, so that. Oh no, hold on. No, it doesn't look like what I want. Come on. All right, let's start from here. Okay, it's good enough. Good enough. A rectangular box. Doesn't look quite perfect, but it's fine. All right, so that's the region. That's the region. All right, so this is 2, -1, 0, 3, 1. Okay, this is your y-axis, your x-axis, and then this is your z-axis. Okay, so this problem is actually easier than the first one. I'm sure you can tell. So, x, y, z squared dv becomes, in this case, all the bounds of integration, all the limits of integration are constants. Since they are constants, you can start with any one. You can start with any of them. You can start inside with x first. You can go 0 to 1 of x, y, z squared dx. And then when you're done with that, you can do 0 or -1 to 2 of x, y, z dy, dx, dy. And then you can now go 0 to 3 dz. Okay? And then you can do them one after the other. Do the iterated integral. Your answer is gonna be, I'm not gonna tell you the answer, but I'm gonna tell you something else you can do. The first method is to just peel off the onion from inside. All right? Do this integral. Then after that, you do this. After that, you do that, But I have mentioned this before, and I'm going to mention it again. If you can separate all your integral two conditions. One, xyz squared, let's do this. Since, let's say, since 1, xyz squared can be separated as the product of x, y, and z squared. In other words, is a product of a function of x, function of just x, a function of just y, and a function of just z. We have this going for us in this problem. Another thing we have going for us is that all the limits of integration, the limits of the region of integration, when I say region, I mean our box B, right, are all constants. If we have this going for us, then we can totally do something something that makes this problem a little bit easier. I'm gonna copy this. I'm gonna copy it. I'm gonna paste it here. All right. So this integral, we can, because we have these two things going for us, this also applies for functions of two variables. But since we have this thing going for us, instead of doing this, we can actually separate it into three different integrals. Look at the z. The interval for z is 0 to 3. We can go from 0 to 3 and then just the z function, dz. Okay? And then we now say, oh, the interval for y is -2 to 2, and we have a function of just y, so let's go -1 to 2. That's what I meant to say, -1 to 2 of y dy. And then we can also say to ourselves, oh, well, you have y for z, you have for x, sorry, that. And then you have 0 to 1 x dx. So you perform each of this integral and then you multiply it. This integral, and this. Perform the integration separately and then you multiply the answers. That's what you do. If you do this, the answer to the problem, what I got is, what did I get? I got 27/4. So I want you to do this problem. You can do it either way, the first way or this way. 27/4. Okay. So let's try another problem. Let us try another problem. So let's evaluate the integral. Now I'm going to use e, square root of x squared plus y squared dv, where e is the region bounded by the paraboloid z equals x squared plus y squared, and the plane z equals 4. All right? So it makes sense to start with sketching our region of integration. Our region of integration is, let's see. Oh no, hold on. Is a paraboloid and a plane. So we start, okay, I'm gonna go easy on you. I'm gonna go so easy on you. You'll be begging me. All right, let's do this. This is y-axis, this is x-axis, and this is z-axis. All right. So we're going from a paraboloid is bounded by this paraboloid, right? And it's also bounded by a plane. All right? This paraboloid is a paraboloid z equals x squared plus y squared. And then there is a whole plane, here, oh no, a plane over here at z equals 4, where z is equal to 4. So this is a plane at z equals 4, right? So if you look at this paraboloid and seal it up with a plane, all you get is just a solid paraboloid. That's all you get. That goes from 0 to 4. So let us solid this up. Solid it up. And this is your E, right? This is the E we're talking about. That's the E. Okay? Now, so we have the Z bound for E. Now, the X and Y bound is the shadow. This casts the intersection of the plane and the paraboloid. The intersection of the plane and the paraboloid is this. That. What do? You project it on the XY plane and you get that. Okay. So let's go one by one. On the XY plane, on the Z plane, on the Z axis, along the Z axis, you have Z is bounded by Z equals 4 and Z equals X plus Y squared, right? And then on the XY plane, you have, let's see, you have the green region, the green on the XY plane. Can you imagine that? All right. So we're familiar with this. Let's see what we can do now. We need to really fully describe our E now. This is E. E is a set of points X, Y, Z, such that Z goes from, Z is between X squared plus Y squared to 4, right? You see that? Now, Y goes from this, right? This line, no, don't do that. My circle is not perfect, but don't shade me. This line, this is the line y equals negative square root of x squared plus 4. No. Let's look at this circle. Let's talk about this circle. This circle is x squared plus y squared equals 4, right? Because x squared plus y squared is equal to z, and the intersection that gives us the circle is where z is equal to 4, all right? So if you come here, what I'm doing is that I'm taking this projection in xy plane and I'm drawing it here, all right? So this is negative square root of 4 minus x squared, and this top part, this is y equals square root of 4 minus x squared. So what do we have? We have that y is between negative square root of 4 minus x squared and square root of 4 minus x squared. See that? And then x goes from now negative 2 to 2, because this is just a circle of radius 2. So x goes from negative 2 to 2. Okay? Now, our integral that we're dealing with, this marvelously looking integral, can now be fully explained. This integral can be fully explained now as z goes from x squared plus y squared to 4. You agree with me? This is z equals x squared plus y squared, and that is z equals 4. Our integral, let's not forget our integral, or integrand, x squared plus y squared. Then we have dz. So we're done with z in setting it up. The next is y. Y goes from negative square root of 4 minus x squared to square root of 4 minus x squared. Okay? dy. And the last one is negative 2 to 2 dx. Again, the most interior integral has two variables. The next one has only one variable. The outer one has no variable. That's how it's supposed to be. If it's any other way, then it's wrong. So we have set up this integral. Just set it up. We've set it up, and it looks a little bit intimidating, but it's not that intimidating. But at the same time, we're not going to do it. We're going to look for a simpler way to do it. I want you to think of the simplest way to do this integral. All right? From something we've done before. It's triple integral, but it has a lot of circles in it. So, something that starts with a P. So I want you to rewrite this integral in such a way that it will make use of the secular nature, the secular nature of our region. All right? Think about it, and I will see you in class. Okay? All right, bye.